This lecture is part of a series of lectures for Rad229 MRI Signals and Sequences offered in the Department of Radiology at Stanford University. The 10th lecture, MRI Pulse Sequences Part 3, is broken down into 3 parts, and Lecture-10B covers echoplanar imaging artifacts. The learning objectives for this lecture include being able to appreciate the challenges associated with EPI, to describe the appearance of 4 principal EPI artifacts, to discuss the origin of these 4 artifacts, and to recall a solution for each EPI artifact. Amongst the many challenges in EPI imaging include the following. There's a signal modulation over K-space that occurs during the acquisition. Recall that in echoplanar imaging, we're acquiring many echoes, perhaps as many as 100 or more, and the signal is decaying during that period of time, either with a refocusing pulse or sometimes in the absence of refocusing pulse. The T2 star decay effects during these long echo trains lead to a modulation of the echo amplitudes as you're filling K-space. You can also have the effects of geometric distortion, which arises from off-resonance sources and also potentially from eddy currents. And these fields will be described further in some of the subsequent slides. You can also have ghosting artifacts, which arise from a mismatch between the even and odd echoes. Recall that the even echoes are acquired, say, left-right, and the odd echoes are acquired right-left, but whatever field effects are happening in the background are constant within the object, and this can lead to some mismatch between the even and odd echoes, as we'll describe shortly. And lastly, chemical shift artifacts are especially problematic in echoplanar imaging, and this is largely due to the fact that we use a very low acquisition bandwidth or effective bandwidth in the phase encode direction. Again, a topic that we'll discuss shortly. So let's think more carefully about signal modulation in EPI. Overall, the problem can be just stated as saying that there is object blurring, and that object blurring is in fact T2 star dependent. So interestingly, it depends on the tissue itself as well. The origin of this artifact is that the T2 star causes signal decay, which is especially large for long single-shot readouts. And again, that decay is going to be tissue-specific, and so we'll see a tissue-specific spatial resolution effect. The solution for this largely relates to shortening the readout as much as possible by using high receiver bandwidths, using the maximum gradient performance, or various ways of undersampling K-space. Anything that helps you image faster will generally reduce these kinds of artifacts in echoplanar imaging, but of course may come at other costs. So let's look more carefully at what's happening. Here we've changed the readout direction, or the phase encode direction, to be left to right. So we're starting our K-space acquisition in this corner here, and we're sweeping in a zigzag trajectory, or an echoplanar trajectory, towards the bottom of our KY trajectory. Now recall, from the beginning of excitation, the transverse magnetization will decay as a function of T2 star, and so the echo amplitudes are getting ever smaller as we go from, say, the top of K-space to the bottom of K-space. On the middle 2 graphs here, I'm just conveying the idea that we move from, say, some negative K-space position to some positive K-space position in the, if this was a bottom-up trajectory. We could also draw this line as a top-down trajectory, both of which are frequently used in echoplanar imaging. This blip direction, though, that is the phase encode steps, which we increment through so-called blipping, occurs quite slowly. And this gives us a low effective phase encoding bandwidth, something we'll look at in just a second. Whereas the stepping in the frequency encode direction is very fast, and so these off-resonance effects, for example, are quite small, or the T2 star effects in the frequency encode direction are quite small. So now, as a function of the echoes that we're acquiring, we begin with a large amount of signal early on, but as the T2 star decay takes over, of course, the echo amplitude is getting smaller and smaller until it may be very close to 0 by the time you're acquiring, many dozens of echoes. But this leads to a modulation of the echo amplitude over K-space, and you could think of it as multiplying the apparent K-space shown here by some window or weighting function that is T2 star dependent. But again, it's also going to be tissue dependent. The off-resonance accumulates in an unusual way as well. Well, if you think about the off-resonance being some background frequency or some background field shift, that field shift will have different apparent handedness as you're acquiring, say, the odd echoes or the even echoes. And so the phase accumulation will sort of be stepwise incremental, say, positively for the even echoes and perhaps negatively for the odd echoes. And this will lead to some interesting artifacts when we start looking at ghosting, for example. So here we've performed some simulations. The simulation here of a perfect object showing various line pairs at high spatial resolutions, intermediate spatial resolutions, and lower spatial resolutions for a range of T2 stars going from 10 milliseconds to 1,000 milliseconds. We can generate this object in MATLAB and simply take its Fourier transform and see that we recover a magnitude K-space that looks like this image that's shown here. We can also simulate an EPI top-down trajectory. That is, we're acquiring this line of K-space and then zigzagging down until we reach the bottom of K-space. And in doing so, we can see that we get a T2 star effect. The top of K-space here is still relatively bright and similar to what we see on the left-hand side, but we can see that it's decreasing in amplitude, especially as we get towards the bottom of K-space here. And this is because the echo amplitude is fading as a consequence of T2 star. But K-space, of course, any point in K-space represents some composite information from the entire field of view. And so the shading is perhaps in some ways not as apparent in K-space as the effect is in image space. And in image space, interestingly, what we see is that for very short T2 star species, say 10 milliseconds, they're very blurred out at the highest resolutions and the intermediate to low resolutions because, of course, of the signal decay, they become difficult to see at all. Whereas the very long T2 star, so 1,000 milliseconds, is unrealistically long for biological tissues. We can see that the spatial resolution is largely maintained. There's no loss because effectively these objects with long T2 star are not in fact decaying for each of the echoes that's acquired. We can also change the trajectory if we want to. So this is an EPI center out trajectory where we're acquiring the middle echoes of K-space and then working our way out incrementally until we finally get to the very edges of K-space. And you might think of this as an approach to minimize this T2 star weighting effect. And the effect it actually has is to lead to more proton density weighted image contrast, because in the middle of K-space, for those very, very first echoes, hardly any of the species have decayed, so they're effectively quite bright. And that actually limits the contrast that's apparent between the varying objects. But as the echoes are still decreasing in amplitude, by the time you get to the edges of K-space, you can see that in this case, both edges are quite faded, which means that spatial frequency information doesn't constitute as much to the object as, say, the original object contained, and this leads to an under-representation of these high spatial frequencies which carry the edge information and consequently result in a loss of resolution. So let's turn the page here now to a different distortion. This is the geometric distortions that are apparent in echoplanar imaging. So the problem is that we can see very large object distortions that can lead to things like signal pileup or signal attenuation or dispersion. The origin of this fundamentally is a field inhomogeneity or a delta B0 shift that's occurring during the long EPI readout. That may arise as a result of imperfect B0. Perhaps we have a bad shim. Of course, we can have susceptibility shifts in our field due to changes in tissue types, air, and more water-like tissues. Or we can also have eddy currents lead to delta B0 shifts that persist during the readout interval. So what are the various solutions here? Well, of course, we can think about careful field shimming. This can be done on a subject-specific basis, and in fact, typically is done on a subject-specific basis. There are various ways to mitigate the eddy currents, either through hardware or specialized pulse sequencing approaches or reconstruction approaches. And of course, we can always think about undersampling K-space as much as possible so that these field effects don't build up during the readout, and that will actually lead to less image distortion. So let's make a comparison of a couple examples. So here's a fast spin echo image. This is an axial image through the head. You can see the eyes here and the brain posteriorly. And here, the K-space diagram on the left is indicating that all of the readouts are occurring from left to right. Now, this kind of approach, a fast spin echo approach, would be relatively slow and might take several minutes to acquire, say, a full brain stack in the case of T2 weighted images with full brain coverage. And if we keep the nominal acquisition parameters similar, we can compare to an EPI acquisition, which would be quite fast because we're acquiring all of the KY lines in a single shot, but the consequence is significant geometric distortion, both in the overall shape of the head, but also in regions of high field inhomogeneity, in this case close to some sinuses that lead to field perturbation. So clearly geometric distortion in EPI can be substantial. So we can look at some simulations of this again. This is a perfect object. In the background, we assume we have some very nonlinear off-resonance frequency shift. And so it's relatively high in frequency here. It's off by, say, 600 hertz, and that's diminishing in some kind of quadratic way as we get to the other corner of K-space. So this is a frequency that's happening in the background while we're trying to image this underlying object. And the consequence is that those frequency shifts will lead to phase accumulation during our EPI readout trajectory, and we'll get these relatively large distortions. And here we can see the underlying phase map for an image of the acquired object, an image of the underlying object, rather. There's an equation that helps us understand and describe sort of how significant or severe these displacement artifacts can be. This is the EPI displacement equation due to off-resonance, and it depends on the change in frequency, which of course can be a function of space. Every pixel can have a slightly different change in frequency. We convert this field to a frequency through the gyromagnetic ratio, and then furthermore to a phase by taking into account what we call the echo spacing, or the time between the EPI readout KY lines, and then multiplying by the field of view gives us units of distance. And so we can use this expression to get an expectation for how large these displacements can be, and it's quite easy for them to be on the scale of many millimeters or even centimeters, largely driven by how large is the background off-resonance shift, and of course what's our echo spacing. So when we can decrease the echo spacing, that's another way to help us decrease the overall geometric distortions that are apparent. So here's two examples. On the left-hand side, this is a body image through the abdomen, showing this is the abdominal wall, and then the liver is over here, kidneys in the back. And in the absence of no shim, this is a pretty distorted, and in fact, because it's EPI, still not a very high-quality image. But when we've appropriately shimmed, that is, we've used the MRI scanner's shim coils and tuned them to even out the B0 field for a specific patient, we can get much better geometric fidelity and overall improved image quality. Another interesting solution for the EPI distortion is using parallel imaging. And parallel imaging is typically thought of as a way to accelerate image acquisition. But another important consideration is that it helps you reduce the amount of time spent in your otherwise long echoplanar imaging trajectory. And so here, as we increase the acceleration rate, going from single shot unaccelerated, where we see quite a bit of geometric distortion, and then increasing to rate 2, 3, 4, and 5, you can see that the geometric fidelity is increasingly improved, especially as we get to rates 3 and above. And so this is a nice approach where the shorter overall echo train length produces less off-resonance, less distortion, of course, the penalty being that it comes with lower signal to noise as well. But there are a lot of clever ways to reduce the echoplanar imaging trajectory to limit some of these artifacts that we're discussing in this lecture. Let's think about another artifact which is also very common in echoplanar imaging, which is Nyquist ghosting. The problem is EPI is prone to field of view over 2 ghosting. The origin generally arises from constant or linear phase offsets that accumulate between echoes, but they oppositely affect or impact the odd and even echoes, again, because we're changing the directionality of the readout for the odd and even echoes in the EPI trajectory. These background phase offsets can arise again from eddy currents, center frequency offsets, or mismatches in the receive system or transmit system, gradient delays, gradient amplifier hysteresis, several sort of hardware reasons why we may have these background phase effects. The solution generally is to limit the center frequency shifts or minimize the echo spacing again, or again, doing whatever we can to limit the requirements or total K-space coverage, for example, using the parallel imaging approaches we saw just previously, will help. So here's an example again of our perfect object, and let's assume we have a constant background phase of this case of a few radians, but the sign of that phase is alternated between, say, the odd and even echoes, and so we have this alteration of the apparent phase in the object as the lines are being acquired. And this will lead to Nyquist Ghosting. This difference in phases between the acquired echoes will lead to Nyquist Ghosting, which is a field of view over 2 artifact. Nothing especially obvious in the K-space data for this particular kind of artifact. So these constant, that is spatially independent phase offsets can cause even and odd echo phase shifts that lead to field of view over 2 ghosts. And generally what you'll notice is that the ghost is relatively lower in magnitude compared to the object itself, but otherwise the appearance of the object, of the alias part of the object, is relatively uniform or well matched to the object's appearance itself. And that's in distinction to Nyquist ghosting that can occur with a linear phase. So here again we have a perfect object, we have some background phase, but the amount of background phase between the even and odd echoes is ever increasing over space, or the background phase is ever increasing over space. And this leads to a different kind of Nyquist ghosting, where you can actually see that indeed you have this field of view over 2 aliasing, but there's also some phase interference that can lead to signal dropouts as well. And so both these constant phase and linear phase effects lead to ghosting artifacts, but of slightly different appearance. One more artifact that I want to talk about is chemical shift effects in echoplanar imaging. And the problem is that echoplanar imaging is susceptible to fat-specific ghosting artifacts. And the origin of this artifact is that fat is chemical shifted relative to water, especially in the low bandwidth phase encode direction. So we'll develop this concept of bandwidth a little bit more in the next couple slides. The solution overall is to decrease the echo spacing as much as possible. That's true of many sort of EPI problems, and also to undersample K-space as much as possible. And if that's still not enough, then fat saturation methods should be considered. We won't talk about fat saturation methods in this lecture, but they are an important component to a lot of EPI protocols. And so let's recall back to just single echo chemical shift effects. Chemical shift displacement artifacts are generally apparent in the frequency encode direction for single echo methods, especially if the readout bandwidth is relatively low or intermediate. You may recall that the spatial shift of pixels that are chemically shifted, that is, say, fat pixels, the amount they are shifted is dependent on the ratio of the chemical shift frequency offset and the receiver bandwidth that you're using for imaging, and then scaled by the field of view in, say, the readout direction. So for a simple example, the chemical shift frequency of fat is nominally about 420 hertz at 3 Tesla, and we might use a receiver bandwidth of plus minus 32 kilohertz and a field of view of, say, 320 millimeters. And this can actually lead to a substantial chemical shift artifact of about 2.1 millimeters. And so at low bandwidths, in this example here, you can see this subcutaneous fat is pretty well misregistered in the left-right or frequency encoding direction relative to the underlying sort of watery tissue anatomy. The subcutaneous fat is brought into registration as the bandwidth is increased, but of course higher bandwidth acquisitions also have lower signal to noise, even though they also have small fat water shifts So as with many things in MR, there's always a trade-off between chemical shift artifacts and bandwidth, for example. Now, chemical shift is not really a problem in the phase and go direction for single echo methods because the chemical shift phase does not accumulate between echoes. But in echoplanar imaging, there's no spoiling between echoes, and so this chemical shift effect just integrates or accumulates between subsequent echoes. So EPI typically uses a very high readout bandwidth. That's to shorten the echo train or the echo spacing as much as possible. But the phase encode bandwidth is much lower and dependent on the echo spacing. So here we can define the chemical shift displacement that we would observe as being dependent on the chemical shift frequency, as we saw in the previous slide, and then the phase encode bandwidth, again, and then the field of view in the phase encode direction. Now, the phase encode bandwidth depends on our echo spacing and perhaps how many shots we're actually acquiring. So oftentimes we're thinking of single shot imaging, so then it really just depends on the echo spacing. So again, a typical off-resonance frequency for a chemically shifted FAT is about 420 hertz. A typical echo spacing is about 1 millisecond. And again, if we're using single shot imaging, then that means our bandwidth and our phase encode direction is only about 1,000 hertz, which is very low compared to what we were just discussing in the context of the frequency encoding direction. And this can lead to very, very large displacements on the order of tens of millimeters or many centimeters, which leads to large fat ghosting artifacts in EPI trajectories. So this is just a simulated example of that. We take a perfect object and we assign an off-resonance frequency for the brightest pixels here to match that of fat. And the consequence is that these fat pixels will shift substantially alias in the otherwise normal appearing image of the object. And so this is clearly problematic, especially as it overlaps with critical anatomy and so forth. And here we're also showing an image of the object phase, where we can see the object phase of the background object is nominally about 0, but the background phase for this chemically shifted fat is, say negative kind of, 3 pi over 4 or something like that, which leads to this large displacement artifact. So in summary, EPI is a very fast but challenging pulse sequence. It's prone to artifacts from off-resonance, T2 star, B0, and gradient imperfections, chemical shift, and more, which makes it challenging. Hopefully this lecture is useful for identifying some of the individual artifacts that will appear in a composite echoplanar image, which of course is susceptible to all of these artifacts on top of one another. Mitigating field effects and limiting the EPI readout duration generally help, but of course they also come at a cost. There's always some trade-offs in terms of increasing or decreasing rather the echo spacing or undersampling the case-based trajectory. Great resources for this topic include these 2 books. I've certainly drawn on them some for building this material. You might be asking yourself, well, what are their alternatives to single-shot EPI? If single-shot EPI is so troubling and problematic, it is a terrific pulse sequence, but it does have some challenges. What kind of alternatives are there? And for that, I encourage you to tune in below to the next lecture, which will cover alternative EPI methods. Thank you.